Okay. All right, guys. Today is actually our 12th meetup at Greenwich AI. This is part 2 of quantum cognitive machine learning and high-yield corporate bonds. Last time we went through some of the basics that would help us better understand and appreciate the work of the paper. And I'm so excited that Joshua was actually available to join us today. Joshua is the first author of this paper that we picked up last time. Without his permission, I added a QR code to his LinkedIn. I,
No problem at all.
I figured LinkedIn is now kind of considered a little okay. So, and yeah, this is the anyone who's interested to the actual paper, you can easily find this if you just type in the title in it. And or if you had any problem finding the paper, let me know and I'll share a link. There's actually a link to the paper on the meeting invite, but again, I can share it separately. And the last slide I have prepared today is to make a small announcement. Today is 1 year of Greenwich AI. Thank you all of you who joined at the beginning or at somewhere midway in this thing we're doing together. I was just reviewing the topics we covered. I put them up here. We started off with interpretability and explainability. Then we moved on we started to get a focus on NLP. We started with RNN, LSTMs. Then we moved on to more attention mechanism. We were focusing on LLM hallucination, how to remove them, knowledge graphs. Then we did some application of NLP for mutual find categorization.
Haley, you got muted.
No, we can't hear you.
Hello, we can't hear you.
Joshua, is this a good time to switch gears to your presentation?
Yes.
Awesome. Thank you so much for being here. Thank you so much for your time. I really appreciate that you made room for this event. Please take it away. And I hear a little echo. Maybe one of your devices needs to be on mute, but
Yeah, I'm just lowering the volume. Thanks.
Of course. Thanks so much. Please take it away.
Thank you so much, Ellie, for organizing and for the invitation, and thanks everybody for coming. I think it's not so easy to find such a large group of people who are interested in so kind of esoteric a subject. So I appreciate you all coming. I think what I'll do is basically just start. So I have two screens to share, but I'll just share the screen on my computer first, just to start with the paper. And I guess I think it looks like I have to send a request to share. So Ellie, do you happen to get that?
I approved it, yes.
Right, cool. Sorry, I've been on WebEx lately, so it's been a while since I've zoomed. Okay. No, wrong screen. Sorry. There we go. No, all right. I'm not sure why it's telling me to. There we go. No, still go. All right, I'll just bring it over here. All right. So sorry for all of the hiccups and the kind of technical difficulties. So I'll just begin by essentially
Sorry, Joshua.
giving.
I'm sorry to interrupt. Before we could see the paper, and now we see your desktop backs.
Oh, really? Okay. There we go.
Now we
Is that
can
good?
see. Yes, we
Cool.
see the paper now. Thank you.
Thanks. Yeah, who knew sharing a screen could be so complicated. Anyway, yeah, so thanks again for the invitation. So I just want to give a bit of an overview of the paper, and then I think because I'll assume that a lot of people in this group maybe don't have a background in quantum mechanics, so I'll just do a bit of a whiteboarding session just to explain conceptually kind of what the fundamental difference is between describing things in a quantum way generally and describing things in a classical way generally. But before we get there, I'm just going to basically describe the financial use case, describe a bit about quantum machine learning, or this particular type of quantum machine learning called quantum cognition machine learning. And then I will, basically get into some of the more details. But I'm sorry, I'm just getting an echo from this other device. It's not letting me turn down the volume all the way. I'm wondering if I can mute this. All right, apparently the volume will only go so low. It's kind of annoying. But anyway, I guess I'll just deal with it. So the financial use case here is basically the following, and it's one that we deal with every day at BlackRock, because BlackRock, one of the biggest asset classes that it trades is bonds. So it's kind of fixed income. And these are particularly relevant for retirement funds, for example, because they're relatively safe assets, compared to stocks. But at the same time, they're also relatively illiquid, so they're harder to trade. And so what will often happen is that a portfolio manager will say, okay, I would like to include this bond in my portfolio because it has the right risk characteristics and it has the right expected yield. So let me trade that bond. But then when he puts the order down to the trader, the trader goes out into the market and says, there's no one taking the other side of this trade. So I just can't trade this bond. And so one natural solution that incorporates machine learning is essentially to look for the most similar bond, right, that the portfolio manager actually will be able to trade in the market. Right, so they basically will look at other bonds that are similar to the desired bonds and try to trade those instead. And so this is kind of the use case is often called liquid substitutes, right? It's basically taking an illiquid bond that you're interested in, but that you can't trade, and then finding a more liquid bond that's similar to it that you can trade. And so this notion of similarity, right, is a big area of machine learning generally, right? Not just quantum machine learning, but just classical machine learning also, right? So the simplest notion of distance, right, in a given feature space in machine learning, for example, is just the Euclidean distance. Right, and you would basically just use the sum of the square distances between the features to compute the distance, or conversely the similarity between two bonds. And other well-known notions of similarity include like the Mahalanobis distance, right, and machine learning is another well-known example. And before we got into this kind of quantum experiment, our team has been working a lot with a particular type of similarity within classical machine learning based on tree-based models, so like gradient-boosted decision trees and random forests. And that particular notion of similarity, right, is what's known as supervised similarity, right? And so there are really two types of similarity. There's supervised similarity, and then there's unsupervised similarity. And the difference between those is essentially that so for example, the Mahalanobis distance or Euclidean distance on a feature space, that's unsupervised, right? In the sense there's no target variable, right? You just have a set of data points in a feature space, right? And the distance between 2 points is just, essentially the sum of the squares of the differences between those features, right? But there's no target. With supervised similarity, the particular notion of distance that you learn over the feature space, right, is guided by the thing that you're trying to predict. So, for example, right, with these tree-based models, right, we learn a notion of similarity between two bonds using a random forest, for example. And that's the kind of baseline model that we use in this paper. And the idea, so just random forests, just a quick introduction, but just for those who may not be familiar. So they're basically ensembles of decision trees, right? So what you will do if you want to make a prediction at a given point is basically just to look at all the training data and average essentially the target variables from the training data that lie within the same leaf of the tree, right? And then you'll average those values over all trees in the forest. So the way we learn a notion of similarity using a random forest, for example, is basically to define the similarity as follows. So 2 points, the similarity of 2 points is just equal to the number of trees in which those 2 points fall in the same leaf node, right, divided by the total number of trees. So it's essentially just, when you look at all decision trees across the ensemble, for what proportion of those trees do those 2 points fall in the same leaf node? And the reason this is a supervised notion of similarity is that, right, where the leaf nodes lie and how those kind of divisions between the leaves are determined, right? That's determined by the target variable in a sense. So 2 points generally will be closer, right, if they also have similar values for the target variable and not just similar values for the input features. So that's supervised similarity, and so in the case of corporate bonds, right, the something close to what we use in production, and actually, we're allowed to share this because it's we kind of would, at least this part of our work is kind of we're kind of in a research division, so there are certain parts where we're just doing kind of fundamental research that's kind of that we share, like this paper. But it's also it's part of the fundamental processes in the company as well. And so what we'll do to form to learn a notion of similarity between corporate bonds is essentially to take all the essential features of those bonds as input features. So for example, the bond's coupon or its credit rating, or the sector in which it lies, and a few other features as well. And those will be the input features, and then we'll use those to predict, right, what the yield of the bond will be, right? So essentially, how much return will you get from that bond, right? And so when you train a random forest or a gradient boosted decision tree to learn a mapping from those bond kind of fundamental features to the yield, right, you learn a notion of distance or similarity on that feature space, right, such that points are closer together, not just if they're closer in the input feature variables, but also if they're closer in the target variable. And so that yield variable that we're trying to predict affects in very significant ways, it reshapes the notion of distance on the feature space in a sense. And so, right, so once we've learned that, right, that notion of distance just using the random forest, right, a trader, right, who's been asked to trade a certain bond but can then basically look at the nearest neighbors, right, which other bonds are closest to that according to this learned metric, and those bonds will basically have similar yields and also similar values for the coupon, the rating, time to maturity, sector, and things like that. And so they'll just say, okay, well, what's the closest bond that I actually can trade in the market now? And so that's essentially the use case, and that's how they use these kind of these random forests to find liquid substitutes. So maybe before I get into the quantum stuff, maybe I'll just pause here to see if anybody has any questions about the use case, in case anything's maybe a little unclear. Okay, yeah, and I guess you maybe discuss. Oh, sorry. Yeah, go ahead, Ellie.
No. I was just unmuting in case I needed to facilitate anything. Yeah.
Okay, cool. Yeah. So I guess you also guys discussed all this maybe a bit last week. So yeah, maybe let's review. So the point of this paper was basically to do the same task, right? Supervised similarity learning. So basically, learn a mapping from the input variables. So same set of variables. So I guess so we have them in here. Actually, I'll zoom out a bit.
Sorry, Joshua, just to,
Sure.
were you using the whiteboard feature up until now?
No, not yet.
Okay.
I'm just going to use that to explain the quantum stuff. Yeah.
Perfect. There was a question, people weren't sure if they should be able to see it, so I think we're good. Okay.
Oh, cool.
Yeah,
Thanks.
thank you.
Right, so the data basically, right, we're just learning a mapping from these features of the bond, right, which are listed here, to the target variable. And here, like, so the target variable for high yield bonds, and those are, high yield means basically like lower credit, right? So, right, if you're going to borrow, or if a company is going to borrow money from you, but it has a lower credit rating, then to compensate you for the additional risk, you need a higher yield in the bond or a higher return. And so, right, these lower credit bonds are called high yield bonds. And for typically high yield bonds will trade on yield, which is essentially just the return to maturity. Whereas investment grade bonds, which are bonds with better credit ratings, they typically have lower yields because there's less risk. So there's there's less compensation in terms of return that's required, right, to the investor, or to the lender. So those bonds are actually traded not directly on yield, but instead on credit spread, which
I'm
is
very sorry, Joshua, to interrupt.
Josh.
I think your microphone moved, so there was
sorry. Is that better?
much better. Thank you. Yes, thank you.
Yeah, thanks. Yeah, so I'll just repeat the part about well, actually, was that just a second ago, or where did I maybe fall off?
I think it's been quite a bit since the previous time I interrupted.
Okay, apologies. Okay, so I'll just go through this again really quickly.
Yes, please. Thank you.
So again, we have these two types of bonds, right? So we have high yield bonds, which are bonds, right, that have lower credit. So that means, if a company wants to borrow money from investors, right, it needs to compensate those investors for the additional risk that they take by giving larger returns on the bonds. So by giving a higher coupon or higher interest rate. For investment grade bonds, right, typically those are not traded on yield, right, but instead on credit spread, which is the difference between the yield of the bond and the yield of the treasury bond of a comparable maturity, right? And so spread is basically just the difference between the yield of the bond and the risk-free yield. And so IG bonds are typically, investment grade bonds are typically traded on credit spread. And so for investment grade bonds, we use credit spread as the target variable, right? And then for high yield bonds, we use yield. But again, the goal, whether we're talking about the quantum machine learning algorithm or a classical machine learning algorithm, is to essentially learn, the kind of functional dependencies between the input variables, among the input variables, and then also in the output variable. The way quantum machine learning or this quantum cognition machine learning works is, so I guess first maybe to dispel a few misconceptions. So there are many different types of quantum machine learning. So the phrase quantum machine learning can mean many different things. Sometimes quantum machine learning means just doing maybe even classical machine learning, but on quantum hardware. But quantum computing is really not at the stage yet where we can really make use of that for practical applications very widely. The type of machine learning that we're looking at here is something called quantum cognition machine learning, and this is a technology that's essentially being developed by a few professors at some of the leading institutions in the U.S. and in Germany. and across the world. But there is a startup that we partnered with called Cognitive with a Q that is basically working on implementing this kind of form of machine learning and selling the technology to various clients. And so we worked on this as a kind of proof of concept to see whether their technology or this new way of doing machine learning was useful for our one particular use case. So this particular type of quantum machine learning called quantum cognition machine learning, right? It doesn't run on quantum computers, although it naturally could. But what's different about it is mainly that it uses a different mathematical formalism to capture patterns in data. So classical machine learning, right, is one sort of mathematical formalism for learning patterns in data, right? What quantum cognition machine learning does is it basically takes the mathematical formalism of quantum mechanics, and instead it uses that to capture patterns in data, right? So there's nothing physically quantum going on, right? When you train a quantum cognition machine learning algorithm, it's just more that we're using quantum mathematics, and in some sense, quantum mathematics, right? The mathematical framework of quantum mechanics is a more general, more flexible mathematical arena, right? Than classical mechanics or than the kind of mathematical framework of classical mechanics. And so, I'll get into some of the details here in a bit, but first I just want to kind of maybe switch over to the whiteboard. So just do that. Okay, are you able to see the whiteboard?
Yes.
Cool. Up the volume here instead. Okay, so right, classical mechanics.
I'm sorry, Joshua, your voice dropped.
Oh, really? Okay. Sorry.
Yeah.
Yeah, sorry. It's I'm getting this kind of feedback from these two devices, so sorry we didn't kind of figure this out more. But this pen is sort of. All right, so in classical physics, right, it will describe something like a particle moving around, right? And we can assign that particle, right, a definite value of its position and a definite value of its momentum, which is basically how fast it's moving and in what direction, right? So the momentum basically tells you kind of, its mass times velocity in a particular direction, and its position just tells you where it is. But those are very sharply defined quantities. Now, in quantum physics, right, the way you would describe a particle like this, so say an electron, or an atom, right, is not as a localized particle, but instead as something that's kind of spread out in space, so like as a wave, right? And the quantum description in some sense encompasses the classical description, because if you take, something like a wave, right, and you zoom out far enough, it looks like a particle, right? So the wave is spread out here, right? But if you were to say, step back really far, right, you would see that basically the wave was kind of localized, in this position. So if you zoom out far enough beyond where you really care about this level of resolution, right, this kind of this like wave packet. So you can think of just like a pulse of water, moving, right? In quantum mechanics, essentially describes particles in that way, right? It's it's a localized disturbance in some medium. And so, right, sorry, okay. But so does that idea sort of make sense that, if we zoom in far enough to say this classical particle, what we'll find is that it's actually spread out, that it's more described as a wave. And so, in position space, right, we'll see that it doesn't have a fully sharply defined location, right? Its location is kind of hazy and ill-defined. And how ill-defined it is essentially determined by the width of this wave packet, right? So it's basically, it's kind of like the standard deviation of this distribution, right? So the way quantum mechanics will describe, a particle like an electron, or even, you could apply it to the moon or to a baseball. But the way it describes, typically something like an electron, right, is essentially by something called a wave function, right, which is just assigns a complex number to every point in space. And so that's just usually designated by this letter psi. And the significance of that function or that wave is essentially that if you take its square magnitude, so it's basically just the square magnitude of the complex number at every point in space, that gives you essentially a probability distribution, right? So you can think of this wave as essentially just a probability distribution. And essentially the quantumness of the particle is determined by how localized this wave is, right? How localized is the probability distribution, right? A particle with a very kind of spread out probability distribution is more wave-like, right? Because it has a less defined location. Whereas, one that's very narrowly peaked, right, is more sharply defined and it looks more classical. So does that, yeah. So maybe I'll just stop there, see if there are any questions about, the kind of broad conceptual distinction between, the quantum way of describing things and the classical way of describing things. Okay, cool. So,
I was gonna.
so if we wanted to describe the position of a quantum
Sorry,
particle, right, which is
Joshua.
described by this wave.
Joshua, sorry.
Yep.
There's a question actually.
Sure.
Yeah, I keep trying to get the wave analysis.
Mhm.
Let's take the ocean, for example. If you're looking at the surface of the ocean, and when the water is, when you're 10,000 feet up, you'll get a very flat ocean. But maybe you zoom in to look at it from 10 feet, you'll get obviously ripples and waves along the ocean surface. Is that kind of the analogy you're talking about?
Yeah, and a bit, yeah. So I guess if you were to think maybe, yeah, let's think of like a water tank, maybe, and if you just have like a localized sort of, so you imagine like a wave that's kind of localized in space and it just travels, and it'll also spread out. But yeah, if you look from say, 10,000 feet up, right, and you look at that kind of, that localized disturbance, right, it'll look like something that's essentially, particle-like because it's centered around a particular location. But if you look close enough, right, you'll see that, at a higher resolution, it actually looks spread out, and it looks like it doesn't have a very well defined location. So basically, as you go to higher resolutions, you see that, even something like a baseball, right? Right. I mean, or you have to really look at its constituents, but like, so like the atoms making up the baseball or the electrons making up the baseball, right? If you look close enough, right, they're not in a sharply defined location. Their location has a certain fuzziness about it. And the way people often, interpret this, this kind of wave function is that they say basically it's the probability that if you were to look at where the electron is, right, you would find it in one location or the other, right? So typically, right, when we talk about quantum mechanics, what will happen is that something like an electron, right, it might be spread out in space, so this wave function, might be pretty spread out. But then when you measure it, so when you actually look to see where it is, what happens is something called collapse of the wave function, which is basically where it becomes sharply peaked at one location or the other. So essentially location becomes exactly localized at one point or another, right? And essentially where it becomes exactly localized when you perform a measurement is proportional to this probability, right? So this psi squared function, so this wave function. So basically this thing, right? So basically the larger, right, the higher the wave is, right, at a particular point, the more likely it is that when you measure the particle, or where you actually look to see where the particle is, it will be, here, whereas it's less likely to be here. And so there are a whole bunch of conceptual issues and philosophical issues, around exactly what that means. But that's essentially kind of the practical rule of thumb that physicists use. Is right. They basically say, when an electron's orbiting an atom, right? It's not in a sharply defined location, but then when you actually go to look to see where the electron is, then it will be in a sharply defined location. But every time you measure it, it will be in a different location, right? And if you look at, essentially the histogram of locations that results from this measurement, what you'll see is that the histogram looks a lot like, it looks exactly like this probability distribution. So this psi squared. And so, right, so these quantum mechanical waves are not waves in the conventional classical sense like that water waves are, right? Because water waves are essentially like disturbances in some medium, namely water, whereas quantum waves are probability waves, right? So it's not that they're necessarily disturbances in a medium, but they're just reflections of where you're likely to find the particle, right? If you observe its location. And yeah, but even if like we have a spread out wave, like this one, that we've been looking at, right? If you zoom out far enough, if say you just don't care about where it is, like, so the resolution that you're looking at doesn't really care about distances that are characteristic of like the width of the distribution, right? Then in a sense it already looks classical, even though it's kind of spread out. If you look at a coarse enough resolution. Yeah, so sorry, I realized there was a bit of a meandering answer, but yeah, I mean, does that help a bit? Or yeah, I mean, feel free to ask a follow-up if that was a bit unclear. Yeah.
Oh no, you're not sucking me in this one. Now I'm starting to think about our sun, our planet Earth, the fact we're moving 76,000 miles an hour through space, but we're also rotating the Earth around the sun, and depending on if your frame of reference is 1 day versus 100,000 years, the probability of where you'll find our planet. Thank you very much. Please continue.
Cool. Yeah. No, I mean, it's true that, yeah, I mean, yeah, there's a whole other area of kind of quantum chaos where actually, yeah, we won't be able to predict, yeah, where the planet will be, if you look far enough in the future. So, yeah, and ultimately that can be attributed to kind of microscopic quantum uncertainties being amplified, right, to a macroscopic level. But maybe to bring this to start to bring it back a little bit to the machine learning aspect of things. So I just want to make one more point about the kind of contrast between quantum and classical physics, that will be necessary to kind of understand how this sort of way of describing things gets carried over to machine learning. And it focuses around what's called the quantum uncertainty principle. And so the idea there, right, is that
I'm sorry, just
Sure.
one more physics point before we leave. I
Sure,
think
sure.
it's worth mentioning that like the quantum principle and the quantum uncertainty doesn't apply to like solar system size object. So when we talk about that we don't know the position of electron, you're talking about the uncertainty principle, which is relevant when we have things Planck sized. It's not really relevant for like say a solar system or things like that. And as you said, quantum chaos is not very well understood in any case, but whether it actually could lead to chaos in the classical sense for, like, say, three-body problems and all that. That's also a little bit unknown, and I'm not sure if we can say that. How
Yeah, so
much
I
we
think
can.
that's a very fair point. Yeah, I mean, so I think that you know, so one point of view, and I guess this is the sort of the point of view that you know, I'm kind of implicitly kind of assuming here, but you're right to point out that it's not fully a consensus. Is that, you know, if quantum mechanics applies to atoms, then it applies to all things that are made up of atoms, right? And so in principle, it ought to apply to planets and solar systems as well.
But I mean, we understand how it becomes classical if you increase the size of the object. That's completely well understood. That in order to see the quantum effect, you really need to be quantum sized. But we know how Schrödinger equation, for example, becomes like Newton equation if the object becomes too large. This is like classical approximation you can take, and it's completely.
You mean like through decoherence and the like
Yeah.
Ehrenfest theorem?
Yeah. For
Yeah.
example, or something like that.
Yeah, exactly.
I would argue that the scale of the universe is way beyond our ability to comprehend. We don't know how everything actually moves through space. And when you zoom into the size of our planet and solar system in comparison to the trillions upon trillions of stars, wouldn't quantum mechanics go to any point in space at any size, from if you zoom out far enough to observe the location of any object in the universe above?
Yeah, I mean, so I think that, yeah, I mean, when you're looking at scales at that large, or even if you're just looking at scales, you know, the everyday, you know, like you know, desks and chairs, right? You don't see effects that are characteristically quantum. But that doesn't mean that quantum mechanics doesn't apply. It's just that essentially to see, so basically physical theories, like, you know, the when you have a new physical theory, right, there will be some domain of that new theory that reproduces the empirical successes of the older theory, right? So when you have a new theory like relativity, for example, right, in cases where objects are moving slowly, right, that will reproduce the predictions of Newtonian mechanics. And similarly with quantum mechanics, right, to, you know, in cases where objects are massive, where there are many particles, where they're interacting with their environments, such that they're you know, there's a lot of interference from the external environment, then right, then in those cases, right, quantum mechanics starts to look like classical mechanics, right? So essentially, what quantum mechanics does is it subsumes basically anything that you can describe using classical mechanics, you can describe more accurately using quantum mechanics. But quantum mechanics also describes a new set of phenomena that classical mechanics cannot, right? And those phenomena are characteristically quantum in the sense that they're right. They are what's kind of distinctive about the quantum way of describing physical systems, right? That classical physics can't describe, and right, and these kind of characteristically quantum effects, right, occur in contexts where you see the kind of, when you're at a level of resolution where you can see the kind of how spread out the wave is, right? But if you zoom out far enough, right, when you look at like the wave we have here, right, it looks like it's localized and like it's a particle, right? So if you go to macroscopic scales, right, although an electron, say, will be spread out, you know, it looks spread out if you look at the level of resolution of like an angstrom, right, at the level of like an atom, right? If you look, you know, if you zoom out, you know, and you really only care about differences of distance of like, you know, a millimeter, right? Then that, you know, the fact that it's spread out won't really matter. So yeah, so basically, you know, but the takeaway is really that the mathematical formalism of quantum physics is really a more general framework that encompasses classical mechanics as a sort of limiting case. And so the idea is to take that same mathematical formalism, right, of quantum mechanics, and to kind of almost encompass classical machine learning as a limiting case. And so just as so just to basically describe this uncertainty principle, because I think that's the kind of last kind of conceptual piece of quantum mechanics that's needed to have some understanding of how this quantum cognition machine learning captures patterns and data. So I'll just briefly describe that. right? So I've already said basically, right, that you know, basically the quantum mechanical wave function, right, is something that can be spread out in space, or it can be relatively narrowly localized. But that's in position space. Now you can also look at things from a different vantage point. So you could look at them from the perspective of momentum, right? And according to quantum mechanics, basically a particle's momentum is essentially proportional to its wavelength. So it's basically a particle that's kind of where its wave is kind of oscillating a lot, right? That will have a large momentum. Whereas a particle a particle's wave function is smoother will tend to have kind of a lower momentum. And so if you know something about Fourier transforms, then basically what quantum mechanics does is you basically have these two domains, right? So you will have say a function in the x domain, right, which is say position, right? But you can express that as a sum, right, over essentially these different wavelengths of some expansion coefficient, and then some kind of Fourier basis, right? So I mean, this is essentially sines and cosines, but it's just a kind of this e to the I, this complex exponential is just a kind of a concise way to represent sines and cosines. And so in quantum mechanics, right, you have two ways of representing the particle, either as this wave in position space, which is basically this psi of x, or and so this is where the axis is x, or as a wave in momentum space, which is this k. Now, the uncertainty principle, what that says is that the more narrowly peaked, so the more accurately you know the position of the particle, so basically like the more accurate, the more narrowly peaked the position is, the more widely spread out the momentum representation has to be. So one extreme would be where you have the wave function of the particle is completely sharply peaked in position, and then very spread out in momentum. Or conversely, you could have something that's completely spread out in position, but very sharply peaked in momentum. And what the uncertainty principle says is that there's a limit to which both the position and the momentum representations of the particle can be simultaneously sharply peaked, right? So the uncertainty principle essentially precludes, right, a situation in which if you're looking at things from the point of view of position, but you cannot have something that's both sharply peaked in position and sharply peaked in momentum, right? So you can't
May I
have
ask something?
this.
May I say something?
Yeah.
Because okay, I think we need to add something to this because not all observables are. You don't get this hazy effect you described all the time. It only happens when the observables are not compatible, in the sense that
Right.
the operators observables do not commute, because
Precisely.
you can come up with so
Thanks for adding that. Yes, exactly.
then this leads to the uncertainty principles, like the Heisenberg uncertainty principle for position and momentum.
Exactly. Yeah, and the uncertainty principle specifically for position and momentum actually is really, it's just a classic result about Fourier transforms. So even if you've never studied quantum physics, right? If you've studied any sort of signal processing, right? If you look at, say, the time and the frequency domains, right? You can have two representations of a signal, right? One in the time domain and one in the frequency domain. And right, there's a fundamental limit to how narrowly peaked, right, the time representation of the signal and the frequency representation of the signal can be at the same time, right? So basically, you would have, if the time representation had a width delta t, right, and the frequency had a frequency representation had a width delta w, right, then that's greater than or equal to 1/2, I think. Don't quote me on the exact number, but essentially, right, if you're looking at time and frequency representations or position and wavelength representations, right, there, the extent to which something can be localized in both representations is limited. And that's actually just a fundamental fact about Fourier transforms. It's not even fundamentally quantum, right? It's just a fact about Fourier transforms, and then actually, and that sort of fact can be generalized even more broadly using operator theory, and so it's not so it goes beyond Fourier transforms as well. Yeah. So and as you said, right, that if you have two non-commuting operators, in this case, right, we have position and momentum operators, then you get this sort of uncertainty principle. Yeah, and so just because maybe the language of operators might be unfamiliar to some people, so maybe it's just worth explaining that, because that will also be necessary. So when you compute, when you have a wave function that's in position space, right, and you want to compute its average location, so right, its expected location, right, what you do, right, is so you just basically you compute this average x, the average, right, which is just this, and that's just computed, right, as an expectation value. So it's just integral ex of x times psi of x squared, right? So this is just the probability. So it's just a classical formula for taking expectations and probabilities, because the psi squared is just the probability. Now you can rewrite this such that you can think of this x as an operator, right? So it's essentially, you can write it as so what this says is basically it's just the complex conjugate of the wave function times x times psi of x, and you can think of this multiplying by x as just like as operating on this function x. And similarly for momentum, if you wanted to look at the average momentum, right, which is essentially on average how fast is it moving, assuming a mass of 1, then what you would have here, if you look in the position representation, right, is, sorry, just sorry, this pen is a little bit, but it's just again psi star of x times the momentum operator, which here is basically a derivative operator, and then acting on psi of x. And generally in quantum mechanics, right, so this is the momentum operator. And generally in quantum mechanics, for any observable or for any quantity, angular momentum or energy or anything like that, right, so we'll call it an observable O, right, that's just equal to, again, integral dx of psi star of x times the operator O times psi of x. So in quantum mechanics, right, if you want to know the average value of a quantity, right, you basically take this the associated operator and you sandwich it between the wave function and its complex conjugate. Yeah, so an important part of quantum mechanics is that because physical systems are represented by things that are functions instead of points, right? So essentially they're represented by things that are spread out. The way you compute a physical quantity, or say its average or any statistics of it, is by using an operator that acts on that wave function, essentially. And now, so the idea, finally getting back to the machine learning, and I realize we only have a few minutes, but I'm happy to stay a bit over. Is that with the input features, right, that you have in your data. So in this case, right, the input features would be these. What you do is you associate an operator to each feature separately,
Sorry, Joshua, if you're pointing to the paper, we're only seeing the light.
Oh yeah. Sorry, I forgot to switch back over. Thanks. Yep. So can you guys see the screen now?
Yeah, yes.
Okay. So in quantum mechanics, basically you associate an operator, just as you do with position and momentum, to each feature, and that operator acts on essentially what's like a wave function, right? So it's what's called a quantum state. So basically you just define this kind of abstract quantity, right? Which is so you define like a Hilbert space, which is essentially where quantum states live, right? And operators are basically just matrices that act on, right? They just act on vectors in that vector space. And so you associate, right, an operator to each of the each of the input variables, and then also to the target variable, the predicted variables. And ultimately the prediction of the model, right? Say if you're trying to predict the yield, right, is essentially the expectation value. So it's essentially this. So psi will be this quantum state, which is essentially like a latent representation of the data. So basically, to each data point will have associated with it a particular quantum state, and in some sense that's like a wavy representation of that data point, right? So just remember, just as with a particle, right, it looks like a point, right? But then if you zoom in, right, you see that it's kind of spread out. And also that there's a certain kind of uncertainty relationship between position and momentum of that particle. Here, when you look at a data point, right, it's represented by a quantum state that's also spread out, but it's spread out with respect to both the features and the and to the target variable. So each data point will have associated with it, a quantum state, just as each particle does. And then just as anything you might want to know about the particle, like its position and momentum, can be represented by an operator. Anything that you might want to know about the data point can be represented by an operator. And so here, right, this operator B is just the operator associated with yield. And the prediction of the model is just essentially the average value or the expectation value of that operator. And so the way we get kind of definite predictions, right, sharply defined predictions, right, out of a quantum description, right, is by doing things like taking expectation values, right? Right. So in the quantum mechanical description, right, if you want to know roughly where the particle is, you take the average value of its position with respect to that quantum state. And here, right, in this quantum description, right, if you want to know what the prediction of the model is, right, you take the expectation value of the target value operator, which is B, with respect to the quantum state that represents the data point that you're interested in. Right. So this quantum state will represent the test point. So it's like a kind of a latent representation of the test point. So similar, like, to in PCA or factor analysis or with a variational autoencoder, right, you have some latent representation of a data point, some reduced kind of dimension representation of a data point. We're doing the same thing here essentially, but in a different way. We represent each data point by a quantum state, and in some sense that is a compressed representation of the data point, right? And if we want to know any of the feature values associated with that data point, right, we have to take an expectation value of the associated operator. And so that's kind of the idea, the general idea. Now, how do you but then the question is, like, how do you train these things? What's learned here? And what's learned is the operators themselves. So these operators, just like as a neural network is parameterized by certain weights or coefficients, right? These operators that represent the target variable and the features, right? Those also have certain weights, right? And essentially the way you learn the operators, right, associated with these different features or with the target variable is actually very similar to classical machine learning. So what you do, right, is essentially over every data point, you so here, right, we have a measure of the, essentially the error. So, what this AK is essentially the expectation value of the operator AK, right? So K basically varies over all of the input features. So the ones that we looked at down here, right? So basically K will vary from 1 to, I guess 10 here, because we have 10 input features, right? And so, and AK is essentially the expectation value with respect to a given point, with respect to a given point of that operator, right? And so this is essentially the kind of model's representation of that data point, right? So essentially, if you take the expected value of each feature, and then also of the target, but if you take the expected value of each feature, right, that essentially gives you an approximate, it gives you an embedding of that data point in a sense, right? In the same way that like a PCA projection would. And so what you want is essentially for the quantum model's representation, right, which is this expectation value, to be as close as possible to the actual numerical values of the data point, right? So your data set will have definite values for the features, right? So this is essentially just minimizing the squared loss or the squared error, right? So in PCA, right, there's a reconstruction loss, right, which is essentially squared error that you try to minimize. And in a sense, you're doing the same thing here. You're minimizing the reconstruction loss, right, which is essentially the squared error between, the quantum representation as an expectation value, right, and the actual value of the features. And so what you do is essentially you train the machine learning model to so you learn the weights essentially so as to minimize this reconstruction error. There's a bit more nuance to it, but that's the general idea. So very much as in kind of classical machine learning, you're minimizing some squared error or something like that. You're doing the same thing here. It's just the way you learn the functional dependencies between the functional relationships among the different variables is different. And so then just to briefly sum up, because I guess, yeah, we're a bit over. Right. So but the idea is that you can use essentially this type of machine learning to learn to do supervised learning, right? To make predictions, right, based on input features of certain target variables, and in turn you can learn that to use that to learn a certain notion of similarity, right, which is essentially based on the quantum mechanical notion of similarity, which is just the inner product between two quantum states. And so the fact that you have this kind of notion of similarity, this quantum notion of similarity, which is the inner product, that will induce, right, a notion of similarity or distance on your original feature space. And so you can basically, once you've learned this quantum model, you can extract the notion of similarity or distance from it. And so then just to sum up the financial results, right? So what we find essentially, so one way to measure the quality of a notion of similarity, whether it's quantum or classical, right, is just to essentially look for any data point, right, look at its nearest neighbors, right, according to that distance metric or that notion of similarity, and say, okay, well, on average, how close are the values of the target variable of those nearest neighbors to the original point, right? Because we want nearest neighbors that ultimately have similar values for the target variable. And so what we find here is that if we, take the k nearest neighbors according to the quantum metric and look at, right, how good they are, if you just take a k nearest neighbors average, you do a k nearest neighbors regression to predict the target variable based on, say, the 20 nearest neighbors, right? The error in predicting the target variable, of those 20 nearest neighbors, where the notion of nearest again is based on the metric that you've learned, right? That does a lot better at predicting the target variable if you use the quantum metric than if you use the Euclidean metric or the random forest space metric, right? And so the idea here is then basically that, right, by using a metric, with this quantum algorithm, learn through this quantum algorithm rather than through more traditional methods, right? The nearest neighbors, the most similar data points to a given test point, will tend to have more, be closer in the target variable. So that's essentially the main result. But yeah, I'll just leave it there. I'm happy to stay over if people want to, but I also, no pressures.
Quick question.
Yeah.
If you can go back to those operators
Yeah.
or the matrices, how many operators are you trying to learn through this?
Yeah, so it's basically one for each of the features and then one for the target variable.
In the total, let's see, 10?
Yeah, so 10 and then 11, right? So for high yield, right? So we have the target variable, which is 1, and then we have 10 here. So that's 11 operators.
I was thinking maybe I'm sure you know more about this, but if you take one operator and then learn it and then use the eigenstates of the other operators, since you know it, and then you can use unitary operators to switch to different matrices without running your algorithm on all the 10.
Yeah. So
Is that a way, or it's not very feasible?
I mean, I guess, yeah. So these are Hermitian operators. So if you exponentiate them, you get a unitary transformation. But I don't know of any practical applications of doing that. Of essentially, taking, forming, say, a unitary operator from, the.
Change the basis of the matrices so that you know more about. Okay, so I don't have a pen. It's hard for me to verbalize these formulas. But okay, let's say you have some operator AK, and then you know the eigenstates of that operator, right?
Right.
And if you form a tensor product of the eigenstates, such that you're changing the basis of one to another.
Right. Yeah. So I mean, yeah, maybe you could use it for a change, like in PCA, right? You also do essentially a change of basis, right? And you find a basis in which it's, essentially all of the, it's essentially in which the correlation matrix is diagonal. It's possible that maybe you could do something similar here, where yeah, you essentially use, a unitary matrix to change, from the basis associated with one operator to the basis associated with another operator. Yeah, so I guess, yeah, because you have essentially a basis, yeah, as you were saying, right, associated with each of these features or with each of these operators separately.
Yes.
Yeah, and so if you wanted to change basis, yeah, I guess you would use some sort of unitary operator. Yeah. But yeah, in terms of practical application, I mean, I would not be surprised if there were a practical application of that. But we haven't come across it yet. Yeah, but it's a very natural thing to do in a way. Yeah, given the quantum formalism.
There's a question from Prakash. He says, he's asking, are you optimizing using gradient descent or quantum way of all paths?
Good question. Just gradient descent. Yeah, so in PyTorch. Yeah. So basically we can use just the standard kind of functionality of PyTorch, right? Because PyTorch essentially allows linear layers, right? So we can just represent these operators as linear layers, and then just optimize, using standard atom RMS prop sort of stochastic gradient descent. Yeah.
Nice. And Sarah asked earlier in the talk if quantum machine learning is computationally more intensive than classical.
Yeah, that's a good question. I mean, this type of quantum machine learning, yeah, I guess in some ways. So basically, we were kind of using Cognitive's sort of API for this. And it does run on GPUs, because I mean, essentially you're you're doing this stochastic gradient descent and aversion, maybe not backprop kind of exactly, but you're employing a lot of the same mathematical operations. So yeah, it is computationally intensive, and more so than a random forest for sure.
I have a question. I really use these things for looking at technologies and concepts and papers for practical applications, always practical. And one of the first things you said about it, it was not so esoteric, but I think it has a very tangible practical application. Please correct me if I'm wrong. What I heard from you is like what it is basically is able to identify assets, or in this case bonds, whether or not what other assets you can trade as a replacement for the bonds that are illiquid.
Right.
So you use these data features that you plug in, and then you say those are the most important aspects of whatever illiquid bond is. Find a different thing that is similar to that will be tradable. So basically something that has a lot more liquidity. In your paper, I really love that you're using something that leverages geometry and the properties of quantum spaces. Very practical application. You can draw that. It's extremely useful to be able to draw that.
Thank you.
And the anomaly detection aspect of it is really, really useful too, because then you can further delve down into the data features and then take out all the anomalies. And sometimes the anomalies might mean something else. Anyway, the implications of this paper is so much more than I think was discussed. My question to you is, do you see any problems? I can't see it. Any problems applying this to not just bonds, because bonds is so narrow.
Yeah, I think I think it's a matter of experimentation, but yeah, I think conceivably, they could be applied to lots of things. My sense is, they did better with the high yield bonds and the investment grade bonds. So, our sense of why that's the case is that this type of algorithm, it does better than classical machine learning algorithms, and particularly random forests, on kind of sparser data. And because of the way it learns the patterns in the data. So I think like it's kind of useful to. I mean, the way I think of the, quantum cognition machine learning is it's it's essentially just like a different family of machine learning models that may be more useful in certain cases or maybe better suited for certain types of data than classical machine learning algorithms, but it may be worse too in other cases. Just because it comes with its own set of biases, like in order to interpolate the data, extrapolate the data, you have to make certain assumptions that reflect the biases in the model family that you're using, right? And this family of machine learning models comes with its own unique set of biases, and those biases make it, I think, particularly suited for describing sparse data. Yeah, because essentially, if you look in that kind of last part of the paper, where we're looking at the distribution of distances, among all the data points, what we found was basically that, for like the random forest distances, right, essentially most points will tend to be pretty far from each other. So if you think about it in terms of similarity rather than distance, right, the number of points that are similar to a given data point, right, in the data set is relatively small. Right, that most points in the data set basically are very far away from a given data point, whereas with the quantum metric, right, the number of kind of nearest neighbors, right, to a given data point is actually much larger, right? So points are kind of closer together, and that just reflects a bias in the algorithm that may be just better suited to certain types of data, in particular sparse data. So that's sort of the way I think about it, is that, you know, it's a new family of models, and it works, and, you know, and it, you know, and it just may be better suited for certain types of data than you know, the kind of classical machine learning algorithms that we have.
Here's some good news. While you were, I'm sorry, I'm a little
Yes.
behind. I'm probably not as smart as everybody else here, but I
Yes.
only heard about the second meetup. And while you were talking, I got a copy of your paper and I quickly read it. I probably missed a few things, but and then I applied some of the concepts you were talking about in your paper into the crypto markets. It actually works quite well.
Oh, wow. Okay.
In two of the marketplaces that I just tried, three.
Oh, wow.
Anyway,
Okay.
so that's good. Thank
Yeah,
you.
very, very, very cool. Well, yeah, the more applications, the better, you know. I mean, I'm sure the guys at Cognitive would be happy to
I
learn
took
from
your
that.
white paper, I threw it
Yeah.
in ChatGPT, and I asked for the exact same thing, the crypto space. And but unfortunately, it's 3,000 characters long. It wouldn't let me paste it into the chat. But I have a PDF response from ChatGPT giving complete instructions on how to apply this to crypto.
Very cool. Yeah, you know, I mean, I think, yeah, I guess it has, you know, crypto, not that I, you know too much about it, but yeah, you know, I mean, it has the kind of some of the similar characteristics, you know, to high yield bonds, in the sense, yeah, that I guess a lot of cryptocurrency, but they're very volatile and they might be less liquid, some of them. So yeah, you know, it sounds like a reasonable proposition to me that,
You
you know, this
call it
might work.
volatile. I
Yeah.
call it, if you put it in a log scale, it's all just noise. If you look at 2010 to present, it's basically a straight line. Get rid of all the noise of the volatility, and you just see a ever increasing, like the prime example of Bitcoin from inception to date. If you forget about all the high volatility variance, this is why Michael Saylor and Strategy are successful to date. We don't know what the future is going to hold, but it's noise. It just keeps increasing.
Yeah, I mean, it's almost, you could say the same thing about the S&P 500 too, I guess, right? That you look at, like, you zoom out enough, right, and it looks like an exponential curve almost, you know, the value of the. But yeah, I mean, what's surprising is that, yeah, and the same is true of cryptocurrency,
So
apparently.
go read a book. You maybe have already read it. Herman Kahn, The Coming Boom.
Okay,
And
it rings a bell, yeah.
what he realized was that early on, with the baby boomers coming, that the stock market was going to do nothing but go up. And if he died in 1981, but he wrote the book in the 70s, I believe. And it's just noise. It's ever expanding.
Yeah, you know, I think that's, yeah, I mean, taking that long-term view where you just sort of you don't sweat too much about the kind of day-to-day kind of, yeah, volatility. Yeah.
There's time horizon, and as we get older, less time horizon is perceived. So therefore, the criticality of what you do in the moment is more so than somebody in their early stages of their life. So
Yeah.
that's another thing. But at any rate, I digress. Your
Thank
model,
Yeah, that's true.
you can feed your paper to ChatGPT and get, and then it's not plug and play, but you have to apply it. But if you take the various data feature sets that you're looking for and then plug those into some type of formula, I think H is absolutely right. It can absolutely be applied.
Yeah, no, that's I think both an interesting and a plausible suggestion. Yeah, I mean, yeah, let me know if you guys ever try it. Because and yeah, I think the, you know, the guys at Cognitive, yeah, would you know, yeah, you
Particularly
know,
good
might
for
be
the
interested in
crypto
it.
markets because there are a lot of marketplaces charts that have low volume, but a
Yeah.
lot of volatility. And for technical traders, it is perfect for this. You know?
Yeah, no,
It's so
that's
good.
a great suggestion.
actually better
Yeah,
than
I would be very curious
application.
to
Yeah.
experiment with that, or if somebody else did. Yeah.
I'm probably stating the obvious here, but as we look at a white paper, it's a static point in time. You look at all the equations and formula, but when you talk about the quantum math of the entire thing and AI, you turn it into a framework, and then AI is ever evolving, ever processing, ever changing with the data sets that it has. And these things are no longer static on white paper. They're just realized continuous.
Yeah.
I'm so sorry to interrupt, but Aaron has his hand up for a very long time. Aaron, why don't you ask your question?
No, I mean, I think from what I see, the paper structure, the CDS market seems like an obvious target market because you already have the features that are, you probably have 70% of the features already. And you would just have to model both sides of the premium risk to come up with pricing, and you could benchmark that against existing static prices from like TIW, from the Trade Information Warehouse, right, which has all the DTCC derivative, captures all that data, maintains all that data.
Yeah, no, I mean, I guess for the same reasons. Yeah, I mean, I think that also sounds like a really, yeah. I mean, we were actually, the next thing we were planning to do was to do municipal bonds, but I mean, I think CDS also, I think is equally, I mean, it's not a market I'm all that familiar with, but given as fixed income, I mean,
Well, yeah, and
yeah,
I mean, the reason I'm really saying it is that you could target the fixed swap market within the derivatives market that then uses the CDS infrastructure to offset risk. So you can, in essence, just leverage, it's really just a continuation of the financial engineering curve that you're on from basic fixed income, from IG to basically complex fixed income,
right.
Um,
Yeah, I mean, I get again, yeah, like
Whereas
super
muni
plausible.
market's
Yeah,
weird because of you have to model the tax duration risk. So it creates all these other, you know, um, you have all this other periodicity risk and also you have to model, or you have to use prior, history of probability to determine tax changes. I mean, basically good guesses of tax policy to determine tax risk because, uh, versus, like I said, versus like if you focused on fixed swap CDS market, like you could probably do that like next week. You know what I mean? It's
yeah. No, I
like,
think and yeah, I think you're
and to be
probably right.
fair,
Yeah.
like, I mean, the data you guys maintain in-house, you could run your own artificial model against prior history to just really do benchmarking, which would just be interesting anyways.
Yeah. No, I mean, I think we're hoping to, yeah, I mean, to kind of continue this POC, and I mean, I think yeah, I mean, you guys are like raising possibilities I hadn't thought of, but I mean, for the same reasons, yeah, I think that it works in high yield, sorry, it should work, in these other markets as well, or at least there's reason to be optimistic about it. But
Yeah.
actually, yeah, I should probably head off just because I
Yeah.
gotta go take
Okay,
care of my
thank you
son.
so
Yeah.
much for being so generous with your time. Thank you everyone for participating.
Thank you
And
for putting it on.
I hope to see you next time. Thank you for staying behind, Joshua. I really
Yeah, no,
appreciate it.
thank you all for coming. It was a lot of
Awesome
fun.
work.
Yeah, and
Awesome
thanks so
work.
much, Ellie, for
Congratulations.
organizing.
Tell your parents thanks for helping you through the decision to learn all the extra math.
Yeah, we'll do. Have a good one.
Cheers.